simple. Electrons are ejecting from the electron gun. Okay, some filament. We are giving some battery, high tension battery and low tension battery to give some voltage to this filament. Then electrons will eject from this metal, this material. Okay, or filament. Okay. After that, we will keep a nickel target here. After that, after hitting this nickel target, yes. Any doubt? Are you asking any doubt or something else? Hello? No doubt? Okay. So these electrons will scatter, and some of them will scatter and some of them will go into deeper into material, and also that will diffract. Okay. To collect this electron, these also electrons we are collecting. This collected to electron. This electron we are taking a circular scale. This scale you can range is 20 to 90 degrees centigrade, 90 degrees. Okay. Here you will have a Faraday cylinder to collect these electrons. Okay, fast moving electrons. Okay. After that, we'll use galvanometer to measure the how much current we got. Okay, how much current we collected. Okay, how much electrons we collected. So once you plot the graph from collected electrons or collected current, intensity of current and scattering angle. Okay, scattering angle. This is scattering angle. Okay, scattering angle, and here intensity of or intensity of current or current intensity, whatever you can write. Okay, so here we are applying different voltage. Here we are applying suppose 40 volts or 50 volts, 60 volts, 70 volts, like that. We are applying some voltage to eject electrons here. Okay, if you increase this voltage, more number of electrons eject from the filament. More number of electrons eject from the filament, and this will reach to the target. And target means here nickel material. This is our target material, right? So after that it will scatter. Okay, so if you increase voltage, more number of electrons will eject from the filament, and these electrons will hit the nickel target. After that, we are collecting these electrons using galvanometer, using Faraday cylinder, and measuring it by galvanometer. Okay, now at 40 voltage we will plot the graph. At 40 volts we will plot the graph. Just it is a, we are changing the angle, theta angle we are changing, and at fixed voltage of 40 volt we are measuring the current. Okay, so this will, it will increase slightly. After that, small bump will observe here. Okay, small bump will observe. That means here current is higher at this point. Okay, after that, again we are increasing the voltage. We are increasing at suppose 44 voltage. This bump is slightly some more increased. Okay, some more increase, and again like that we are increasing several voltages. Okay, at several voltages we got at 54, maximum bump is observed at 54 voltage. At 54 voltage we got the bump is maximum intensity. Okay, this bump intensity is maximum at 54 voltage. Okay, at 50 degrees, at 50 degrees, at 54 volt we got maximum voltage. Okay, now if you increase further, if you increase the voltage further, what happens? This bump size is decreasing. Again, if you increase this voltage, the bump size is decreasing. Suppose 68 volts. Okay, 68 volts. The bump size is decreasing. Okay, why? This is only at 54 volts we are increasing. At 54 voltage and 50 degrees, we are getting the maximum intensity of the current. Okay, so here see in the diagram, first diagram, here we are increasing the voltage, right? Once you increasing the filament voltage, more number of electrons eject, and more number of electrons reach to the nickel target. After that, it will scatter in different direction. But at 50 degrees centigrade, at at 50 degrees, this theta, this is theta, right? Incident angle and scattered angle is the theta. Some angle of 50 degrees, we are getting the maximum intensity, where at 54 volts. Voltage is 54, and angle, angle between incident rays and scattered rays is 50 degrees. At this angle, at this particular 54 volt, the bump size is, we got maximum bump size at this position. Okay, beyond, if you increase further voltage, the bump size is decreasing. So How we got this bump size increasing, decreasing? We measured current intensity, right? Using galvanometer, we measured the current. Okay, from there you can plot the graph, which angle and for which voltage you are getting maximum current, and after that you plot the graph. Okay. Now, so what is the wavelength of for a charged particle electron? What is the wavelength? De Broglie wavelength for electron. What is the value? De Broglie wavelength for electron. What is the value?
H by MV.
Sorry.
H by MV. H
Sorry.
by MV.
That is okay. For in case of second case, we have solved, right? In charged particle, for electron, we have solved, right? Did you remember that? For
It's
electron,
by root 2.
12.26 by root V, right? V is the potential. Okay. And this lambda in terms of angstrom. Okay.
Potential.
Yeah. This V is the potential. I think you remember this one. Okay. Now, here see, we know this value already electron we calculated, we simplified the expression. So now you substitute here in this expression 12.26 by where we got the maximum current in the graph. This is maximum intensity at 54 volts, right? Where we got maximum current?
Yeah. 54 volts.
Yeah, 54 volts. We got the maximum. Bump is increasing means what here? What is the y-axis? Intensity of current. The bump is increasing means more number of electrons reaching the Faraday cylinder. So more current we are getting. That means more number of electrons flowing to the Faraday cylinder. Flow of electrons only current. Okay. So at 54 volts we are getting maximum current. Just you substitute here 54. So what is the value? Just do it calculation. If you have calci, do it. What you will get? T. Are you solving? Are you solving? Please solve it. Just let me know answer. Chapati, are you solving? 12.26 by 7 into 7.
7.34.
How much, Amma?
7.34. Root
Yeah,
54 value.
7.34. Okay, just if you don't know calci also, approximately you can estimate. Suppose 7 into 7, 49, right? That means 7.1 or 2 like that you will get. Okay, here 7.34. So if you substitute this one, how much you will get? 1710.
1.6.
67, huh?
1.668.
668 means 67. Okay,
Yes,
let's
sir.
take 668, 1.67 or 68. Okay, approximately. Okay, so 1.67 or 68 angstrom, right? So using this Davisson Germer experiment, if you incident these electrons on nickel crystal, okay, nickel crystal, using this voltage, using some voltage potential, we have observed the wavelength of these electrons or wavelength of this material particle is lambda is equal this much, right? 1.67. Now this, so here you can see this. Here if it is difficult to understand these graphs, I will draw one more graph. So here the graph is angle, this is scattering angle, this is number of electrons. So we are measuring number of electrons as a function of angle, so this will increase like this at 50 voltage, 50 degree centigrade, like this at 50 degrees centigrade. This is suppose let's 50 degrees, sorry, 50 degrees. At 50 degrees we will get the maximum number of electrons at 54 volts. At 54 volts and 50 degrees and 50 degrees we are getting the maximum number of electrons. Okay, that 54 volts we have substituted in the wavelength formula, that is lambda is equal 12.26 by root V. After substituting, we got the value 1.67 angstroms from this one. So now we got the value this one. Now what we will do, what we have to do, so now we'll draw the nickel crystal. Okay, nickel crystal planes. Okay, like this. Suppose we have nickel crystal, we'll experimentally we will prove in using X-ray diffraction technique. Okay, X-ray diffraction techniques. Okay, atoms are aligned in a systematic manner because this is crystal. Okay, this is crystal. Atoms are aligned in a systematic manner. Okay, now we are in this is some normal to this planes, right? Normal to the this plane. So we are this is some normal. So this is some incident electrons are coming from electron gun. After hitting this film nickel, some of the reflecting back, and so if you incident some of the electrons, this will deep go inside and it will also diffract back. Okay, here the spacing is about how much here for nickel. If you take nickel, d spacing is d is equal 0.91 angstrom, that is approximately 1 angstrom. So that's why the slit with this is also like slits, right? Suppose if you have any small slit, if you send any light here, you will observe a diffraction pattern, right? Here you will observe some diffraction pattern on the screen, isn't it? So this small slit here also, this spacing between atoms act as a slits. What is that? You have seen diffraction grating, right? Grating. Have you seen this grating? Anybody seen the student grating while doing optical measurements? Have you seen grating? No, no. I think in this semester you will do experiment. Suppose a diffraction means if you send some light through a small slit, you will observe some intensity pattern. Okay, intensity pattern like this. Okay, that means this small slit, if you send the light, it will uh, bends towards the edges of the slit. Here also the spacing between atoms is about 1 angstrom. So this small spacing between atom act as a slit. That's why when you send the light, if these two rays are in same phase, this first ray and second ray, or first electron beam, second electron beam in same phase, there is a constructive interference. When first and second is out of phase, these two are destructive interference. When this constructive interference happens, we get the maximum intensity. Suppose this is 25 degrees centigrade. If you take 25 degrees centigrade, so they proved first they made incident with the angle of 25 degrees centigrade. So if it is 25, what is this angle? What is this angle? This is also 25, right? 25 degrees, and this is the planes. This what we are calling this one. This is one plane. This is second plane. This is atomic planes, crystal planes. This we are calling crystal planes. Crystal planes. Crystal planes, and the what is the angle between this plane and this normal? This is 90 degrees, right? So what is the angle of this ray? This one, what is the angle now? What is the angle? This is 25. This angle is 25. The total is 90. Normal to these planes. This is crystal plane, first plane, and this is
65 degrees.
second, 65, right?
65.
Yeah, very good. Thank you. Okay, this is 4 planes I have drawn. Okay. Planes means, okay, atoms are aligned in a systematic manner. So one, if you take one line, that is plane. If you take one order of this atom, it is a plane. Okay, here also I have drawn 4 planes. Okay, each plane atoms are arranged very systematically. So spacing between two atoms is about 1 angstrom. Okay, suppose they incidented this light with 25 degrees centigrade. So this the angle between this normal to this first ray also 25, and this is 65, right? So total is 90. This is 25, then this is 65. Now where we are getting diffraction between these two rays. between these two beams. Okay, then here we are not getting anything, but these two rays, once we send like this, okay, this when these are in same phase, this will get constructive interference and intensity will be maxima. Here diffraction intensity will be maxima. After that minima, like this we will get the pattern. Okay, so when you understand this diffraction pattern, okay, when you understood diffraction pattern, see, suppose first ray and second ray in same phase, equal phase, there is a constructive interference. Constructive interference. That time, if you see diffraction pattern, here we will get the maximum intensity. Okay. After that, there is a small intensity peaks. Okay. After that, small intensity peaks. Why we got this maximum here? Maximum peak. How we got this maximum peak? Why we got maximum here? So, are you following?
Yes, sir.
When two optical rays or electron beams are light in same phase, they are in same phase, there is a constructive interference. Constructive interference means the phase will be sum up. That means intensity will be added or summed up. So intensity will increase for constructive interference. Suppose they are out of phase, there is a destructive interference. Destructive interference, that means the intensity will decrease. Intensity will decrease. Constructive interference, intensity will increase. Okay, here also we are when electrons are sent, electron beam, or you can say light or whatever. Okay, so here also when you send 25 degrees centigrade the incident light, there is a constructive interference. This first second beams are same phase and we are getting a constructive interference. Constructive interference means this first light and second light are in same phase. Constructive interference happen, the intensity also increases. Why this is we are calling diffraction? Because we are incidenting light, the atomic spacing between these two atoms is 1 angstrom, about to 1 angstrom. So it act as a small width of slits. It act as a slits. The spacing between two atoms is act as a slit. These two spacing between two atoms act as a slit, so that we are observing diffraction phenomena in a crystal, in any crystal. Okay, now we observed at 65 we got the maximum intensity or constructive interference between first light and second light, or first electron beam and second electron beam. Suppose this is happens to many planes, but we have drawn only to understanding first two planes only we have drawn. Okay, after that the Bragg's X-ray diffraction condition, Bragg's X-ray Bragg. Okay, Bragg's X-ray diffraction condition. What is the X-ray Bragg's diffraction condition? Do you know Bragg's diffraction condition? We have discussed this one. Did you remember?
Initially, the light.
Yeah, very good, very good, very good. N lambda is equal 2d sine theta. N lambda is equal 2d sine theta. So we are taking diffraction order of first order diffraction. So n is equal to 1. So lambda is equal to d sine theta. So here d is the atomic spacing. So what is the value? D is equal 0.91 angstrom for nickel crystal. So this spacing will change for different crystal. It will be different. So nickel crystal it is 0.91 angstrom. What is the theta value here? 65 degrees. 65 degrees. At this degree, 65 degree, we got the maximum intensity. We got the maximum intensity of diffraction pattern. So substitute these values. Lambda is equal to D is equal to 0.91 angstrom and sine 65. Sine 65. This is the diffraction angle. Theta means here diffraction angle. That means where we are getting the diffraction phenomena, at which angle we are observing diffraction phenomena. That is the Bragg's diffraction angle. Bragg's diffraction angle. Okay. Now at the 65, we are observing diffraction phenomena. Okay. So now, so at this substitute value, what is the value here? Just calculate it. What is the value? What is the sine 60? If you don't have calculator, just sine 60 value. What is the value? Sine 60. చెప్పండి ఎవరు చెప్తున్నారు?
Q/2.
Root 3 by 2. Okay, very good. Root 3 by 2 means root 3 means 1.732 by 2. That means how much? Point 8 something, 8 something, 81 something, right? So here 65 means just it value maybe increase, maybe 3, maybe 4, like that.
0.906.
0.9 వచ్చిందా? Okay, 0.9. Okay, 9 something like that. Okay, if you calculate, what is the value here?
1.63.
1.63 na?
Sir.
1 point around 65 you will get, because we have neglected this decimals. If you take decimals, approximately we will get 1.65 angstrom. Okay, using this diffraction condition, we observed wavelength is 1.65. But using experiment, what is the value? Lambda. Just before Davisson Germer, we have solved, right? Lambda is equal 12.26 by root V angstrom. How much we got here? Value 1.67 angstrom. Yeah, very good. Okay, now if you compare these two, so using Davisson Germer experiment, we got the wavelength of electrons. What is the wavelength of electrons? Is 1.67. Using the X-ray diffraction condition, we got the wavelength of 1.67. So from this equal values, from this analysis, so electrons are behaving as a waves. Electrons are behaving as a waves. That means electrons are matter waves. Electrons are matter waves. Okay. Electron is having, how these are matter waves? Electron is having mass and they are having velocity. These are primary need, primary requirement for matter waves, and they are showing, these electrons showing diffraction pattern, diffraction phenomena. Okay, diffraction phenomena, and using this diffraction phenomena, they are showing wavelength. If you estimate the wavelength, this wavelength and diffraction condition, also wavelength is same. So this division experiment proved the electrons behaves as a matter waves. Okay, is this clear? Now what is the main using now I will explain one more time. First